Welcome to the problem-solving session for Chapter 24. Let's begin with question 1. Question 1 asks us to determine the net torque through the surface of a cube which has sides L and is located in a region where there is a uniform electric field along the I-hat direction. Well, of course, we know the cube has 6 faces. They're showing us 4 of the cube's faces. 1 with a normal along the minus I-hat direction, 2 with the normal along the positive I-hat direction, 3 with a normal along the positive J-hat direction, 4 with a normal along the minus J-hat direction. If we could draw a 5, it would have a normal along the K-hat direction, and a 6 would be back here with a normal along the minus K-hat direction. So, let's see. We notice that there is no charge inside this cube, and therefore, all the lines that come in through the back side, electric field lines, go out through the front side. So let's begin with face 1. In face 1, we see that we have an electric field which is in the I-hat direction, but when we take a dot product of the electric field with the area normal of region 1, because they are at 90 degrees to each other, we get a contribution of minus EA. The minus comes in because the cosine of the angle between the electric field and the area normal is 180 degrees. Let's go to face 2. Face 2, E dot dA for the area normal 2 gives us EA. Why? Because the electric field is in the I-hat direction, and this time the area normal is also along the I-hat direction. Let's look at 3. In this case, the electric field dotted with the area normal for face 3 is equal to 0 because the angle between the electric field direction, which is in the I-hat, and the area normal of face 3, which is along the positive J-hat direction, make an angle of 90 degrees, and the cosine of 90 degrees is 0. Likewise, we can say the same for face 4, because the angle here again is 90 degrees. We could say the same for face 5. Again, the angle between the electric field direction and the area normal is 90 degrees, and the same for the last phase where E dot dA is, for number 6, is also equal to 0. So we can now be assured that the net electric flux through this cube equals 0. But of course, we would have suspected that anyhow, since we know that when an electric field passes through a closed surface, the number of lines that come in equal the number of lines that go out. Next problem. Here we're told there is a Gaussian surface which is a sphere and it surrounds a point charge cube. We're asked to determine what will be the value to the electric flux when the following changes are made. So let's go ahead and draw our Gaussian surface with a charge inside, which of course we know, therefore there will be an electric field which is radially outward cutting through the Gaussian surface, and therefore we will have a flux, an electric flux, that is equal to the charge inside divided by epsilon naught. Okay, well, in part A, they say, what if we triple the quantity of charge inside the Gaussian surface? So in other words, if by some way we could replace the single positive Q with a Q, which is 3 times the value. Well, in this case, the revised electric flux, call it electric flux prime, would be equal to 3Q over epsilon naught, and 3Q over epsilon naught is 3 times the original electric flux. In part B, we're asked to determine what happens if the radius of the sphere is doubled. Well, you can see that in using Gauss's law, there is no dependence whatsoever on the size of the Gaussian surface, or even for that matter, the type of Gaussian surface, as long as it's closed and as long as the charge is inside. All that matters is that the electric flux can be measured by the quantity of charge inside divided by the permittivity of free space. So in this case, we can say the flux remains constant. Likewise, in part C, if we change the type of Gaussian surface, the electric flux also remains constant since it has no dependence on the shape of the Gaussian surface, only on the charge. Okay, well, lastly, what happens if we take the charge, Q, and we move it to another point, but also inside the surface? Here again, provided that the charge is inside the surface, the electric flux remains constant. Next question. We have the following charges located inside a submarine. Now, of course, a submarine is a closed surface. Q1, 5 microcoulombs. Q2, negative 9 microcoulombs. Q3, 27 microcoulombs. And Q4, negative 84 microcoulombs. We are asked in part A to determine the net electric flux through the submarine. Well, the net flux will of course be due to the total or net charge which is inside the submarine. Well, that's the sum of all of the charges that we have just listed. Well, when we substitute the numbers, 5 minus 9 plus 27 minus 84, we get minus 61 microcoulombs divided by 8.85 e to the minus 12. And that gives us a value of flux, which is negative 6.89 e to the 3 Newton per meter squared over Coulomb. So what does this mean to have a negative flux? Well, it means that when we take into account all the positive charges added to all the negative charges, we are left with a net quantity of negative charge. And therefore, there are more lines that come in through the submarine than go out, and therefore our flux is negative, and that is reflected by the sun. Now, something which I'd like to do so that we gain a little bit of practice here is, let's just say that instead of discrete charges, we were to have, let's say, a line of negative charge. This line of negative charge is quite long. In fact, has a total length capital L. Now, we wish to put a Gaussian surface around this line, and let's go ahead and make it a cylinder. We are going to place a cylinder so that the axis of the cylinder corresponds with the position of the line. Now, we know that the electric field will point towards the line because, of course, the line is negative, and therefore, if we could visualize the electric field, this is what it would look like. Now, the cylinder is not as long as the line itself, and in fact has a length little l. But the line has a uniform charge density, so that the total amount of negative charge, which is on this line, divided by the total length of the line, equals the total amount of negative charge that is located within the length of the cylinder. So when lambda is a constant, the ratio of charge to length is a constant number. And so if we ask ourselves, what is the flux through this Gaussian cylinder? The answer is, okay, what is the Q, which is inside? Well, we know Q is going to be equal to, we can write it this way, we can write it as minus lambda times L divided by epsilon naught, or if we happen to know the total charge and the total length, we could write Q, or minus Q as the case may be, as minus Q, and here the minus is just to indicate that the charge on the line is negative, little l over big L times epsilon naught. So if the lambda is what's given to us, then, and we know the length of the cylinder, we use this expression for Q in. If, on the other hand, we happen to know the total charge, the total length, and we're given the length of the cylinder, then this would be our choice for determining the charge inside. Next question. Here we're told that there is an insulating solid sphere of radius A with a total charge Q, which is positive. And we're asked to determine, here's the total Q. We're asked to determine the electric field at certain locations. Now, we're also told that the charge Q is uniformly distributed in the interior so that all points radially outward contain more and more and more charge. So the charge grows until we get to the total, which is right on the surface of our sphere. Okay, so the first question tells us to find the electric field at a point in the interior of this sphere. Well, let's see. Let me choose green here. And in the interior means that our Gaussian sphere, and yes, it will be a sphere because that matches the symmetry of the charge distribution, is going to have a radius which is smaller than the radius of the actual sphere. And so here we are concerned with what charge is inside our Gaussian surface. Well, it's not going to be big Q because the charge grows up to the maximum of big Q when we get to the surface. So how do we determine what the charge is? Well, we make use of a piece of information that was given to us earlier. They told us that the charge was uniformly distributed. And what that means is that the ratio of the total charge over the total volume is constant. Well, if this is constant, that means that the total charge over the total volume equals a smaller quantity of charge over a smaller volume. In fact, the volume of our Gaussian sphere. And so we can write little q, the q inside, over 4/3 pi, r cubed, equals big Q over 4/3 pi a cubed. Since these two ratios are equal, we can now write Q in terms of big Q, the total quantity of charge which was given to us. So we divide the 4/3 pi, since it's common to both sides, and we write big Q times r cubed divided by a cubed. Now we are ready to proceed with finding the electric field at a point inside. Well, let's see. On the right side, we want to write our Q in, capital Q, r cubed over a cubed, and of course we've got an epsilon naught here. On the left side, we note that the Gaussian sphere has a surface area 4/3 pi r squared, and of course the area normal of the Gaussian sphere is parallel to the electric field. The electric field is everywhere constant over the surface, and we see that the radius squared of the Gaussian surface cancels two of the r cubed associated with the charge. Notice here that charge grows from the center as a constant times radius cubed. Anyhow, we're ready to write our expression for the electric field. The electric field will be given by Q times R divided by 4 pi epsilon naught a cubed. Now, 1 over 4 pi epsilon naught is equal to K. And so another way that we may write this expression would be K Q R over A cubed. And of course, this is in the radial direction, so we put our unit vector R hat. And we note that for some given quantity of charge Q, K being the electric constant, A cubed being the radius cubed of the sphere, E only depends on R. Well, let's go ahead and substitute our numbers, and we get E equals 8.99 e to the 9 times 26 e to the minus 6 coulomb times 0.1 meter, that's our Gaussian surface, the radius of our Gaussian sphere, which is where we had to determine the electric field, divided by 0.4 meters, the whole thing cubed. Of course, that's the radius of our charged sphere. And we get a result of 3.65 e to the 5 newtons per coulomb in the r hat direction. Now, in part B, we are asked to determine the electric field at the position r equals A. Well, when we look at this expression here, when r is equal to A, E is equal to, let's put our K, let's use this expression right here. KQ, R equals A, 1A here cancels one of the denominator, and so the expression becomes KQ over A squared R hat. And this is just the value of the electric field at the point where we are exactly on the surface of the sphere. All of the charge of the sphere is within our Gaussian surface, and so we can find the electric field, and in fact we'll find that it's the maximum value of the electric field. 8.99 e to the 9 times 26, e to the minus 6, we'll go ahead and write it with powers of 10, divided by 0.4 meters, the whole thing squared. And this gives us a value of 1.46 e to the 6 newtons per coulomb. And it certainly agrees that when we compare it to the value of the electric field inside the sphere, we get a larger value. Well, what happens as we get outside the sphere? In other words, when R is greater than A? Well, in this case here, all of the charge, we're going to have it now, let's go up a little bit. We're going to have a Gaussian surface, which is out here, and therefore all of the charge of the sphere is going to be contained inside our Gaussian surface, and therefore the Q in, if we start with the right side, will be total Q over epsilon naught E times the surface area of our Gaussian sphere, and this gives us an expression that E equals 1 over 4 pi epsilon naught is K Q over R squared in the R hat direction. So now we just need to substitute our numbers. E equals 8.99 e to the 9 times 26 microcoulombs, e to the minus 6 coulombs, divided by the radius of the Gaussian surface, which is 0.6 meters squared. And that gives us a value of 6.49 e to the 5 newtons per coulomb R hat. And it agrees with what we said because it is smaller than the value which was on the surface. So the electric field is always largest along the surface. Next problem. Here we are given an insulating ring which is hollow on the inside, has a radius of 0.14 meters, and a total charge of 32 microcoulombs. The charge only sits on the surface of this shell. So this is a hollow, very thin shell, and all of the positive charge sits only along the surface. There is no charge inside. Well, you can guess what's going to happen when we try to determine the charge inside a Gaussian sphere. And again, the sphere here, because it matches the symmetry of radius little r. Let's go back here and indicate radius A of the shell. If you ask yourself, what is the charge inside here? Well, there isn't any. It all sits on the surface. So when R is less than A, we see that Q in is 0. Well, using Gauss's law, if the right side is 0 and 4 pi R squared, which is the area of the Gaussian surface, can't be 0, it must mean that E has to be 0, because something times something which is not 0 is itself 0. Okay, what about when R is greater than A? This time we take a Gaussian surface which has a radius R bigger than A, and of course here you can see that the entire charge on the surface of this hollow sphere is inside, in other words, the Gaussian surface, the Gaussian sphere. And so E times 4 pi R squared, this time equals total charge over epsilon naught. We put in our numbers. We recognize that 1 over 4 pi epsilon naught is Q. E equals K, Q over R squared in the R hat direction, 8.99 e to the 9 times 32 e to the minus 6 divided by 0.2 meters squared, which is the radius of our Gaussian sphere, and we get a value of E, which is equal to 7.19 e to the minus 6 Newton per Coulomb in the R hat direction. And again, I'm hoping that my calculations, the numbers I'm getting from my calculator, match yours. And if they don't, you might want to just double check that I didn't have an input error. Okay. Next problem. Here, we're told that there's charge that is distributed over a long line of charge, and that the charge per unit length is equal to minus 90 microcoulomb. For some reason, our minus is not showing up here. So this line has negative charge throughout, and we want to choose a Gaussian surface that matches the symmetry of our line. And of course, the negative is everywhere on the line. It's one-dimensional, so it has no radius itself, and it's very long. Therefore, we don't have to consider any fringing on the ends. Well, we're going to choose a Gaussian cylinder as our surface. Our Gaussian cylinder is going to be L long, and we'll have a radius R, little r. And of course, that radius corresponds to the location where we're being asked to determine the electric field. And we note that the electric field is everywhere inward and perpendicular to the curved portion of the cylinder. Notice, however, in the top and bottom of the cylinder, the electric field coming in like this is perpendicular to the area normal. So here E and dA are perpendicular. Here E and A, or dA I should call it, make a 90-degree angle. Okay, so of course we know we're going to have a net flux. Well, that's all right. That will be given by the negative sign right here of our charge distribution. Here at the top, electric field comes in like this, and the area normal comes in like this. So here again, we have zero contribution. So essentially, when we use Gauss's law, we are going to have a contribution from the top, E dot dA. That's going to drop off to 0. A contribution from the bottom, E dot dA. That's going to drop off to 0. And the contribution from the curved portion, E dot dA, which will not be equal to 0 because the angle between the electric field and the area normal is not equal to 0. In fact, it is negative, but of course that will be taken into account by the charge inside. So what is the charge inside? Well, since it's a uniform charge distribution, we know that it's going to be the density of charge times the length of the cylinder. So our Qin is, in this case, let's go ahead and write it here, E times the curved area of the cylinder, pi r squared times L, equals lambda times L over epsilon naught. This is the curved area of the Gaussian cylinder. This is the charge enclosed by the cylinder. We see that the L's cancel, and in fact, E, radially, everywhere radially inward this time because it's negative, is given by lambda divided by pi r squared epsilon naught. Oh, let's see, is it 2 pi r squared? Let me see here. Am I missing an expression here? Oh, sorry, this is not pi r squared. Uh-oh. This is 2 pi r. Oh, common mistake that we don't want to make, and that is the expression for finding the area of the curved sphere. So let me go ahead and get rid of that. 2 pi r. The L's still cancel, so it's lambda over 2 pi r epsilon naught in the radial direction. It'll be radially inward. And let's go ahead and plug in our numbers. And let's see. They wanted us to get the electric field at 0.1, 0.2, and 1. Well, we'll go ahead and just do 1 because the other is just a matter of we'll see that the electric field drops off as 1 over r. So let's go ahead and find the electric field at the position 0.1. Well, we've got, we can actually multiply both sides here by 2 lambda, 2 times 2 pi r epsilon naught, so that we can get a 1 over 4 pi epsilon naught here, and therefore write k times 2 lambda over r. And that will just save us a little bit of work in terms of entering our numbers. K is 8.99, e to the 9 times 2 times negative 90 e to the minus 6 coulombs per meter, divided by 0.1 meter, and of course this will be the r half direction, and we get a value of electric field minus 1.62 e to the 7 r hat direction Newton per coulomb. Well, this concludes the first part of the problem-solving session for Chapter 24. See you next time.